In this episode, we will discuss one of the techniques of feature engineering and its importance in data science and machine learning. Feature engineering is the term that refers to a set of techniques that are applied to data before the data is used in creating models. Why we should perform feature engineering? Because it improves the efficacy of the data to produce the desired effect. If a dataset is used without feature engineering, it may not produce the desired effect, and it can also make the learning difficult. In this episode, we will talk about one technique of feature engineering known as feature scaling. Feature scaling brings several benefits to the learning process. It increases the learning speed when used with local optimization methods, particularly with first order methods like gradient descent. It can also avoid issues with numerical stability in second order methods. Now, it is important to note here that feature scaling is not a single algorithm. It has been implemented using many different algorithms depending upon the data distribution and the use case. One of the core reasons behind feature scaling is that it can result into a cost function surface which has less elliptical contours. Let's understand how the elliptical contours are a bit problematic for the learning process. When we perform the cost or the error minimization, the gradient descent direction always points perpendicular to the contours of a cost function. When minimizing, if the cost function has elliptical contours, the gradient descent direction will point away from the minimizer of the cost function, and this will lead to zigzag steps back and forth. This zigzag nature forces us to reduce the learning rate parameter alpha. If you transform the contours of the cost function more circular, then the gradient descent direction will be more towards the minimizer of the cost function. This will result into smoother steps and you will have opportunity to increase the learning rate. From a point of view, you can consider standard normalization as an optimization trick that improves our ability to minimize virtually every machine learning model. One of the popular methods or algorithms for feature scaling is known as standard scaling, also called standardization. Let's understand how this is implemented. Basically, it is a simple two-step process. In the first step, you perform mean centering. For each input feature, you compute the mean value and then subtract it from each element of that input feature. Algebraically, you can think of it as xi minus mu, where mu is the mean value and xi is the ith element of the input feature. In the second step, we perform rescaling. That is, for each input feature, we compute the standard deviation and use it to divide each element of the input feature. Note that standard normalization on an input feature makes sense only if that input feature is non-constant. A constant value input feature will have zero standard deviation and therefore division would not be possible. Such input feature should be removed from the dataset because it does not contribute in the learning process. When you test your model on the new data point, remember to use training data's mean and standard deviation to standard normalize the test data point. Now, standard normalization does not bound the values to a specific range. It is not like the values will fall between 0 and 1 or between -1 and 1 only. In scikit-learn, you can use the standard scaler class available under pre-processing to perform the standard normalization. Now, what we have noted so far is one algorithm for feature scaling. There are many such feature scaling algorithms that are useful in different circumstances. The selection of these algorithms is mainly dependent on your original data's distribution. Let's talk about another algorithm called min-max scaling. In this algorithm, we first compute three values. First, we identify the minimum value in the input feature. Then we identify the maximum value in the input feature. And then the third, we identify the difference between minimum and the maximum value. Once we have done that, then we subtract the minimum value from each element in the input feature and then divide the result by the difference between minimum and the maximum value. Now, comparatively, if you see, min-max scaling bounds the data in a range. For example, between 0 and 1, you can change this range to -1 and 1 also. Let's take a real life situation. Suppose there are few outliers in your dataset. In such a case, the min-max scaling will perform poor because the values are bounded in a range. It will severely reduce the scale of non-outlier values compared to outlier values. So outlier values will take the maximum value that is available in that range. And this will make the outliers heavily dominate the learning process. In such cases, standard normalization can perform much better as it does not bound the values in a range. Now this is the case where you have very few outliers. Now let's take another case. Suppose you have a data set and when you look at its distribution, you find that it has a heavy tail. Heavy tail means there are significant number of values going far away from the distribution's mean. In other words, you can also say that the tail is not due to exponentially rare values. In such cases, both min-max and standard normalization will not perform well if applied directly. Ideally, you should transform the data in such a way that it reduces the heavy tail, and then you can apply min-max or the standard normalization. In other words, you can say that making the data distribution fall into a roughly symmetrical shape. For this, you can take log of the data if the distribution tail is really long. That log data distribution will be more symmetrical compared to the original distribution. Now there is another advanced method of feature scaling called PCA-Sphering. It is also known as whitening. In this method, we first rotate the mean-centered dataset such that the largest orthogonal directions of the variance, that is the top k principal components, aligns with the coordinate axis. This rotation is done prior to scaling each input. Now the benefit of whitening technique is that it can make the contours of the minimizing cost function more circular, thereby providing easier gradient based optimization. But this method has a higher computational cost as it involves computing the PCA and rotating the dataset before scaling it. In this episode, we noted 3 feature scaling algorithms: standard normalization, min-max scaler, and PCA-Sphering or whitening. If you note carefully, you will find that data distribution plays a major role in deciding which algorithm to choose. And further, data distribution mandates to go for the feature scaling.